Welcome back to H20 Special Relativity. In this video, we talk about Galilean transformation. So what is it we want to do? We want to describe our event P, maybe Professor Klute exploding, with two different reference frames. We can call one of the reference frame our laboratory frame. Maybe that's the frame in which Professor Klute was stationary. It has an origin and has axis X, Y, and Z. And then we have a moving frame, which is moving with a constant velocity with respect to the laboratory frame. The origin is O prime, the axes are X prime, Y prime, and Z prime. All right, so now what do we learn from this? Let's think about an example. An example most of you have experienced before is the one where you sit in a train car. And if it's not a train car, it can be a car or a plane, something which is moving with respect to Earth. If you look out of the window, and the acceleration is very, very minor, it's often not clear whether or not the Earth, the train station, or the train car is moving. And so you have this kind of weird feeling that, I don't know if maybe the neighboring train started moving or I'm moving. But what we want to do here is describe you sitting in the train car, reading a newspaper once within your laboratory frame, within the frame of the train, and then we want to describe the very same events or sequence of events in the frame of the stationary train station. All right, let's look at a specific example. Here again, our professor is exploding at a time Tp at xp, yp, and zp. To make this a little bit easier, we define at time t equals 0, the origin of the two frames coincide. That just means that at the origin, we have two clocks, two watches, and we make sure that they're synchronized. Right, and then my watch stays with me, and then there's a second watch, maybe with you, which moves along. And those are great watches; they're synchronized. We also want to simplify. We can always define the direction of our coordinate system such that the velocity, the relative velocity between the two reference frames is in one specific direction. Here I decided to use X. I could have used Y and Z, and I could rotate the coordinate systems or the relative movement of the coordinate systems in any way. It's just a simplification here. When I do that, I can rewrite this event P in the S prime frame through the S prime in the following way. So for X, we find that XP is given by X prime P is given by XP minus V, the velocity, relative velocity. I could put a little label X here, times TP. And then for the Y coordinates and the Z coordinates, there's no change. For the time, intuitively, you say that these two watches, they run with the same speed, meaning that the time in both frames for the same events are the same. So now I'm asking you, if you're watching this video, to find the velocity and acceleration. It might be good to stop and just write this down. So find the velocity and acceleration of the S prime expressed by the S coordinates. So let's try to do that. So first we build the derivative dx prime dt prime, which is our velocity. That's the velocity of an object in my prime frame. And that's given by d dt. I can just do that here because the times are the same, times x minus vt. That's x ux, the velocity in my S frame, minus v. That's really what you expect. You just subtract or add the velocities. If I then build the acceleration, I have to build the derivative of ux prime, which is our acceleration in the primed frame. Here again, I just do this in x direction because the solution for the y direction and z direction are trivial. So now I find dux dt minus dv dt. Now the velocity as we defined between the two reference frames is constant, therefore this is 0, meaning that the velocity, the accelerations in the two frames are the same. The accelerations are the same, that means that the forces in the two frames are the same. And that means that the forces or the accelerations are invariant. They do not change based on the reference frame I use. So now, coming back to the example we discussed in our very first lecture, your experiment in the train car. As the velocity between those two frames, the frame in your car or a second frame are constant, there is no way to tell whether or not your train car is moving or not. That is only true as long as the velocities are constant and unchanged, constant. So in summary, in Newton's mechanics, time and accelerations are invariant, and therefore also the forces. There is no inertial frame which is above another one. So you can pick one or can pick another one. There's no difference in the descriptions of the physics between those two frames.